Hello, I'm Quinn Morgan. I'm a recently graduated master's student. This is work that I completed as part of my master's thesis. This is Quantifying Digitizer Design Requirements for a Sediment-Generated Noise Instrument. All right, so first off, I want to talk a bit about the background area and where this research fits into my field. My field is about acoustic detection of bedload transport. Bedload transport is all the rocks, gravel, large sediment um, that moves down a riverbed as the river flows. It's pretty important for habitat conservation, specifically of northwestern salmon. They require a specific size of rock to spawn in. If the rocks are too large, they'll beat themselves to death trying to knock the rocks up. And if they're too small, it'll crush their eggs. So changing bedload transport will change their habitat. Other categories are sort of integrity of bridge foundations and emergency response, as well as other like hydrological research. Unfortunately, tracking bedload transport, the state of the art to get a direct measurement, is to drop a net into the river and count the number of rocks that you collect and do a grain size distribution at a lab. That process is pretty expensive. You have to send like 3 or 4 people out there, and time consuming, as well as you get a pretty low temporal resolution. You can only do this maybe once or twice a season. So the need for a remote sensor is pretty important. Some non-direct sample methods are using a mechanistic model based on discharge. So as the river goes up, you can get an estimate of how much bedload might have transpired, but that's not a direct measurement. We want to have a sensor that directly measures bedload. Another one is pressure plate sensors, but I'm focused on acoustic detectors. So an acoustic detector of bedload transport looks like a hydrophone, which is an underwater microphone. So everything you know about microphones is pretty much the same. It's just underwater. This picks up the acoustic signature of the interparticle collisions. Laboratory experiments have shown, and some theoretical assessments have shown, that the peak frequency of the interparticle collisions is proportional or inversely proportional to the size. So larger rocks will make a lower frequency sound and smaller rocks will make a higher frequency sound when they collide. The two kind of open questions in this field of like acoustic detection of bedload transport is like, what features for SGN, which is sediment generated noise, best represent bedload? And the second one is, how do we validate these methods? What this work focuses on is what is the bit depth and sample rate necessary to pick up these features. The study area is in just sort of middle of Oregon, sort of near the Salem area. It's located right, let's see, is this right here. That's our location at Greensbridge in Jefferson County. It is downstream of 2 dams. So some of this research is done in the French Alps, where they have lots of movement of bedload. In our little area, there's not quite as much, but we do get some. I gotta click this. Whoop. So the specific hydrophone system that we're using was designed by the United States Geological Survey. It involves an Aquarian audio H2A XLR hydrophone attached to a Raspberry Pi Pico, Raspberry Pi Zero W, and data is stored on an SD card. There's a battery and some other logging equipment there. The recording is 1 minute every 30 minutes over the course of a handful of months. That's the rainiest season, so we get sort of high flows and some low flows to confirm that bedload is happening at the higher flows. All right. So motivation for this work specifically. Ideally, we want to design a low-powered instrument to just set it out there and essentially forget about it and just get updates about what bedload we're getting at what time. And the first step to do this is to define what sampling rate and what bit depth is necessary to perform this analysis. Reducing the sample rate by, say, from 44 kilohertz to 22 kilohertz would reduce the number of writes you would have to do to your SD card. And that's where most of the power happens in these types of systems, is writing to the SD card. Additionally, the bit depth will also reduce the size of the files, same with sample rate. So there's a storage saving and a power saving if we can minimize the bit depth and the power consumption. Additionally, it'll make it cheaper. A lot of the devices that are used for this are either repurposed oceanographic hydrophones, which are really expensive in the thousands of dollars range, or some put together instrument that scientists have built, and they could be spending their time better used doing science than just hacking together a lower cost like Raspberry Pi system like this one is. So those are the two like motivation for this. The actual methodology for how I'm going to do this is I'm taking a whole bunch of data, all the data that we've collected over those few months, and extracting features, or I will take the 44 kilohertz 16-bit PCM data wave, extract 3 different features from it, and then quantize and downsample the wave and extract the same features. And then compare the extracted features with the gold standard. This is going to be done at 4 different sample rates and 5 different quantization levels. And we've decided that a median difference of 5% is sort of deemed acceptable. Bedload estimates, when compared to like direct samples and like models or mechanistic models, are about within 3 orders or 3 times an estimate. So a difference of 5% is not going to make much difference where the literature is at right now. Okay, so the features that I'm taking out of the features I'm selecting for the first feature that I'm selecting for this type of analysis is a impulse detection method, which essentially just does takes a spectrogram with 3 millisecond windows and 25% overlap and Hamming window, and then checks to see if the spectral centroid is between 1 and 3 kilohertz. This is sort of trying to detect an interparticle collision, which has been shown to like the peak frequency is between 1 and 3 kilohertz, at least from this the study that this is based on. And then if the energy of that collision is above a certain level, then we count that as a detection. And our feature here is the number of detections in a given 1 minute of audio. The second feature, based on the paper written about the Trinity River, which is a really large scale study where they mapped the acoustic signature or these features onto a whole bunch of different direct samples to make a mechanistic model based on the audio signature. This is a spectrogram as well, except the feature is the mean of all of you take the mean of each frequency band and then just sum between 1 kilohertz and 6 kilohertz. And that's your feature, is that single number. The acoustic mapping feature, this is a type of method proposed to replace direct sampling. You do like an acoustic mapping, which is you place a hydrophone on top of the riverbed and you record for a minute or so and make an estimate of the bedload that's moving at that point. But the hydrophone, instead of being stuck into the river, is sort of at the top. That's what this method was originally designed for. And you take the median power spectral density and then sum above 2 kilohertz. So you take a median of each frequency band and sum up above 2 kilohertz. So quantization and decimation. After I've got these features out of the 44 kilohertz 16-bit signal, I reduce the bit depth by just zeroing out the least significant bits. So for example, 11, which is represented 1011, will go to 8, which is 1000. Decimation is performed by low pass filtering at the new Nyquist rate. So if you're going from 44 kilohertz to 22 kilohertz, you'll need to perform a anti-aliasing filter at 11 kilohertz, because that's the new Nyquist rate to eliminate those signals. Then you downsample and then resample using the Fourier method, which is just you perform a Fourier transform, add zeros at the end, and then an inverse Fourier transform to bring it back. That procedure is just to normalize the results over different sampling rates, so you're not having to do a more complex adjustment. And there isn't any information added since you're just padding it with zeros. So the results for impulse centroid, this is the sort of detecting the exact impulses. We got a sampling rate down to about 11 kilohertz, was sufficient to meet that 5% median difference. And same for bit depth to about 12. Right here on this line, the ones that the specific files that pushed it over when we were investigating a little bit closer looked like they were at pretty low flow rates, so around 400 or 4,000 to 5,000 CFS. And we're pretty sure there wasn't bedload there at that point. So this is one point to keep in mind for our results, at least. Like that. Whoops. There we go. Okay, second one, the Trinity River. So same for here. Our sampling rate when dropped down to 11 kilohertz was well below the 5% median difference, and now down to 10 bit depths was also sufficient. The interesting thing about these results is that it gets worse when you go to 22 kilohertz, and then better when you drop down to 11 kilohertz, which is this is an area for future exploration to see why this is. And the bit depth performed better than the impulse centroid. The median bedload, so the acoustic mapping feature, was very clearly quite at 12 bit depths and then shot off after that. And the sample rate also down to 11 kilohertz. So overall, the minimum bit depth and sample rate to meet the 5% threshold, with the exception of the impulse centroid, is 11 kilohertz, which is sort of 1/4 of what's standardly used, and 12 bit depths, which is down from 16. So some questions remain are sort of why that Trinity River feature improved at an even lower sample rate, and then also how do other sediment-generated noise features perform under this analysis. There's quite a few others. Future work could also investigate trying a higher sampling rate with the same procedure, and then also automatic gain control during the quantization step to make that a little bit more robust. I want to thank the USGS PSU partnership for funding this research. Thank you very much.